people. Hope we're doing well today. This winds up being the second video. We're going to basically show everything for this function right here and then graph as accurate a sketch as we can from that information. Now, some of you are looking at that and going, that looks pretty familiar, and it should look familiar. We've discussed ones like this before. This is actually a serpentine function. If the x were missing and it were just 8 over x squared plus 4, remember that would be which of Agnesi, right? But the x added to it creates a graph that looks something like this, right? Or no, something like it kind of comes in and does that number, okay? And if you're thinking to yourself, how can I possibly remember that? Well, because we talked about it several times, and we'll continue to talk about functions like that, because it's kind of neat. Now, what you're thinking is, gosh, another one with symmetry. Well, yeah, I tend to do a lot of examples with symmetry, because we can only firm up our understanding of symmetry if I give you symmetrical graphs. Now, don't expect every single one on the test to have symmetry, because I do recognize that I do quite a few in class and in the videos that have that symmetry. But now, let's go ahead and talk about domain. Now, I know that this is a rational function, but it's one of those unique and rare rational functions where the denominator will never be 0, right? Because basically, remember, the definition of domain is the set of all possible inputs. And if I look at that function and I say, okay, what values of the input, in this case x, what values of x are impossible? And the answer is none. There's no radical, so I have no negativeness of a radicand to deal with. And that denominator, while denominators, I have to watch out for them being 0, this one will never be 0, because x squared is always non-negative, and non-negative plus 2 is always positive. So if there is nothing that is restricting what numbers I can plug in, what values of the input variable I can use, then basically it's negative infinity to infinity. It's all reals. Now the range is a bit trickier here, right? Because I basically need this minimum and this maximum value before I can actually fill that in. So we're going to have to come back to that once we deal with once we do the extrema from the first derivative sign chart. Let's go ahead and talk about x-intercepts. Now, I've already told you that it's like this, but you can go ahead and use your normal tricks. You can basically set this equal to 0, and of course, you'll find out that this is equal to 0 because it's a fraction when its numerator is equal to 0. And so you'll get an output of 0, 0. And so the y-intercept and the x-intercept wind up being, of course, the same. It's the origin because this goes through the origin. Now, there are no other x-intercepts. If there were, there would have to be more factors in that numerator, more distinct factors, and there aren't. Now, let's go with symmetry. Symmetry, I noticed that the numerator is odd, the denominator is even, but let's say that you didn't actually recognize that. You can just run through the test, basically plug in a negative x, so I get 8 negative x over negative x squared plus 2, and that winds up being negative 8x over x squared plus 2. Well, that means that y of negative x is equal to negative y of x, and that basically means that it's odd, okay, that it has origin symmetry. Now, let's go ahead and talk about asymptotes. Now, of course, there are no vertical asymptotes. So asymptotes, no vertical asymptotes, because there's no breaks in the domain, right? So there's no, and of course, vertical asymptotes are not the same as end behavior asymptotes. Vertical asymptotes are sort of like existence asymptotes. You're saying the function doesn't exist here. But end behavior asymptotes are different. They basically say, as x gets really, really large in this direction, the graph tends to look a lot like this graph, this right here. And in this case, the end behavior asymptote winds up being y is equal to 0, right? And you get that simply from taking, the limit as x goes to infinity of 8x over x squared plus 2, that's 0. and the limit as x approaches negative infinity of 8x over x squared plus 2. That's equal to 0. That gives us our end behavior asymptote. So we found our domain. We're going to wait on the range. We found our intercepts, both x and y. We've identified the symmetry as being origin symmetry, and we have basically identified that there are no vertical asymptotes, and our end behavior asymptote is y is equal to 0. Now, what we need to do from here is we need to go ahead and find the derivative. Now, it is a quotient, so we're going to be dealing with the quotient rule, and that's probably not fun for some of y'all still. But when we're doing this, we start with the denominator. All right, start with the denominator, the derivative of the numerator, and then of course the numerator times the derivative of the denominator, all of that over the denominator squared. Now, when I simplify this all down, it's going to be 8x squared plus 16 minus 16x squared, blah, 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 blah. It basically simplifies down to 2 minus x squared times 8 over x squared plus 2 squared. Okay, well, I notice that my numerator, I need to basically determine my critical values based upon where my derivative is either 0 or undefined. Well, all that happened to this denominator was it just got squared in the derivative. So there's still no place where this is going to be undefined according to its first derivative. But it is going to be 0 someplace, right? So the critical values come from setting that factor of 2 minus x squared equal to 0, and that of course gives you x is equal to plus or minus root 2. So let's go ahead and do a first derivative sign chart. Oh, and I can probably squeeze it in right here since there's only basically 2 places where it's chopped up. We have negative infinity to negative root 2. X is equal to negative root 2. I have, sorry, that shouldn't be there. Negative root 2 to root 2. X is equal to root 2 and root 2 to infinity. And that is the way that we carve up the domain for the first derivative sign chart. I know that these two are 0. That's kind of how I got them. Now I'm going to plug in representative values. Now I know that negative root 2, if you don't know this, you should, is 1.414. Okay, so a representative value for this interval could be negative 2. Now, I'm not really worried about the denominator. The denominator is always going to be positive. 8, of course, is a constant. It's always going to be positive. The only thing that has the potential to change sign is this right here. And if I plug in negative 2, I'm going to get 2 minus 4, or a negative. If I plug in 0, which is a representative value of this interval, I'm going to get 2 minus 0. That's going to be positive. And if I plug in positive 2, again, it's going to be exactly the same numerical output as here. It's going to be negative. So what I have here is that. And that, we've already talked about the fact that this is a serpentine function. That actually does kind of look like what it should look like on the first derivative sign chart. So we need to go ahead and discern the two things that we've been asked to discern from the first derivative. We know that it is increasing only on that small interval negative root 2 to root 2. It is decreasing from negative infinity to negative root 2 union root 2 to infinity. Now, there's your intervals increasing and decreasing. Let's identify our maxes and mins. Let's say we have a minimum at, and of course, if we're going to deal with a minimum, we have to basically plug it back in order to find the corresponding output. It's better to go ahead and do it right now. If I plug in negative root 2 into here, we're going to get negative root 2 into here, we're going to get oh, we got to plug it into the original function. Okay, so we plug in negative root 2 into here, and we're going to get 8 times negative root 2. Plug it into here, and you're going to get 2 plus 2, or 4 in the denominator. So it's going to wind up being the ordered pair, negative root 2 negative 2 root 2. And we know that it's a min because y prime changes from negative to positive. And then our max, well, since there's symmetry, it's pretty easy. It's going to be root 2 and positive 2 root 2 because y prime changes from positive to negative. And there we go. Now, I'm going to go ahead and start on a fresh sheet of paper for the second derivative. It's not going to be, too terrible, but it is, of course, we're going to need to deal with it in terms of the quotient rule. So, here we go. That is the first derivative. So the second derivative, and this is going to be a little bit messy, but you should be able to do this by now. You are big bad calculus students. We're going to start with the denominator, and then we're going to take the derivative of the numerator. Now, if you want to think of this as 8 times, 2 minus x squared over x squared plus 2 squared, that's fine, and sort of leave the 8 out here to be multiplied by the second derivative after you take the derivative, that's fine. Or, of course, you can think about it as 16 minus 8x squared over x squared plus 2 and include it in the numerator. It doesn't really matter either way. I kind of like the whole idea of the 8 sort of sitting out in front, so I'm going to do it like that. Now, so basically I'm going to take the derivative from this form right here. So the 8 just sort of comes along for the ride, as coefficients do. So I have the top minus times the derivative, the bottom times the derivative of top, minus 2x, minus the top, 2 minus x squared, times the derivative of the bottom, which is 2, x squared plus 2, and then of course a little bit of chain rule action. Got to put the 2x in there. Now, that of course, the denominator gets squared again. But remember that that numerator up there is 2 terms. And I know that this and one of these is common and can be canceled with one of these in the denominator. Okay? So what I want to do from here is let's go ahead and keep that 8. This winds up being times, we can go ahead and multiply all this out. This winds up being negative 2x cubed minus 4x. I almost put 2x, but now if this is negative, let's go ahead and make it a plus and put the negative in here so that we don't forget to distribute it, right? So this becomes 4x in here. 4x times negative 2 is negative 8x, and 4x times x squared is 4x cubed. That's x squared plus 2 cubed. You still have this 8 sitting out here. That becomes 2x cubed, right? Because these two combine, minus 12x over x squared plus 2 cubed. And that, of course, can be 8. Actually, it can be 16 if you want to. Pull the 2 out. 16 times x, and then, of course, that's x squared minus 6. So that winds up being, not terrible, but, just a little bit of work. A couple places where you could wind up having a careless error, losing a negative, like I said, like not properly distributing this minus, which is, plus a negative across this binomial that occurs here on the right-hand side of that numerator. But when I get here, I notice that my critical values, again, have nothing to do with the denominator. Despite the fact that this is cubed, you know that x squared plus 2 is always going to be positive. So that denominator will never be 0, and therefore there will never be a point at which the second derivative is undefined. The only thing I'm worried about is when will the numerator be 0, and it's basically when x is equal to 0 or x is equal to plus or minus root 6. Now I have 3 critical values for the 3 critical values for the second derivative, so I'm going to need to carve up my domain into a few more pieces than I did previously. So it's negative infinity to negative root 6. X is equal to negative root 6. Negative root 6 to 0. X is equal to 0. 0 to root 6. X is equal to root 6. And root 6 to infinity. Now, go ahead and draw the dividing lines for our chart. We know that these are 0, and now we simply need to evaluate each of these intervals. We need to evaluate the positiveness or negativeness of the second derivative in these intervals using representative values. Now, negative root 6 is 2.449. We recognized that earlier, right? Or on the last video. So if it's negative 2.449, negative 3 is a representative point in here. So if I basically plug in negative 3 into here, and if we're going to be using this form to evaluate it, because it's easier, right? So we're going to plug in negative 3. Negative 3 in this one right here is going to be 9 minus 6, so it's going to be positive. But that one right there turns it negative. It's negative. In here, we can use negative 1 as a representative point. Negative 1, and then 1 minus 6 is negative 5. That's a negative times a negative in that numerator. We get a positive. Plug in positive 1, we're going to get 1 times negative 5. And of course, if we plug in positive 3 into here, we're going to get 3, and then 9 minus 6, or positive 3, and that's going to be positive. So down, up, down, up. Now, what we need, of course, also is we need to find out where the original function actually is, like what outputs it has at positive and negative root 6. So let's go ahead and we can do that. Remember that the original function is y is equal to 8x over x squared plus 2. Now, if I'm going to go ahead and plug in, let's plug in positive root 6, and we can extrapolate back to negative root 6 because of the symmetry. That's going to be 8 times root 6. Well, if you plug in root 6 down here for this x in the denominator, it gets squared and just becomes 6. So it's 6 plus 2 in the denominator, which is 8. The 8's cancel, and it just winds up being root 6. So what you have is root 6, and negative root 6, negative root 6. So let's keep that in mind. Let's go ahead and deal with the concavity that we need to read off of the second derivative sign chart. We know that it's concave up on negative root 6 to 0, union root 6 to infinity. We know that it is concave down from negative infinity to negative root 6, union 0 to root 6. And we know that we have 3 points of inflection because y double prime changes sign at all second derivative critical values. Okay, and those 3 points are going to be 0, 0, negative root 6, negative root 6, and positive root 6, positive root 6. So I have everything that I need in order to go ahead and sketch this curve. My scale is going to be a little bit different than it was on the first video. Okay, I do have values that get, I mean, I guess I could draw a little bit, but I want to see a little bit more of the curve as it goes out, you know, past 3, you know, to 4 to 5 to 6, maybe even to 7. So let's go ahead and scale it down just a smidge. But we're gonna, since there's symmetry, we obviously need to put the origin as close to the center of the plane that we have. I think I kind of eyeballed it, and I think that's sufficient. Okay, so instead of doing 4 squares for every unit like we did in the last video, we'll do 2. We'll still be able to sort of do some estimation. -1, -2. So yeah, each hash mark that I'm drawing is 1 unit. Okay, let's start just plotting the points that we found. Now, remember, 0, 0 was our only intercept. It also winds up being a point of inflection, so that's kind of handy. Let's go ahead and move on to the critical values. Now, remember, the critical values that turned into maxes and mins, the minimum was at negative root 2, which is negative 1.4, negative 2 root 2. Well, that's just twice that, so it's negative 2.8. So you have negative 1.4, which is almost at negative 1.5, and then negative 282, so basically you have that point right there. And since there's, origin symmetry, you're going to have roughly the same thing right up here. Okay, well let's move on to the points of inflection, because those are going to be handy as well. The points of inflection wound up being at negative root 6, negative root 6. So remember, that's negative 2.449, so almost negative 2.5, and almost negative 2.5, and so you get that point right there. And again, over here, same sort of thing, you get that point right here. Okay, now, we don't have to settle for just those points, because we can sort of t-chart a couple of more if we want. Now, if I were to go ahead and plug in 1 into here, I would get 8/3. 8/3 is 2 2/3, and so that winds up being kind of right about there. That shouldn't surprise us. Okay, and we're probably not the most helpful piece of information in the entire world. Let's go ahead and figure out what happens at 4 over here. Okay, if I plug in 4, that's going to be 32 in the numerator. 32 in the numerator and 18 in the denominator. 32 over 18 is going to be 16/9. Probably not the easiest thing to deal with, but 16/9 over here at 4. Remember that 18/9 is 2, so 16/9 is going to be just below 2. And that kind of tells you how fast, once it hits this maximum, and then hits this inflection point, how fast it's going to basically flatten out as it goes off to infinity and negative infinity. And so I'm going to use a pencil again, just to make sure I can erase if I make a mistake. So it comes up here, okay, so this is our maximum, and I'm going to turn it a little bit. And this is still concave up, but once it hits here, it starts to flatten out, right? So concave, decreasing and concave down doesn't last very long before decreasing and concave up takes over, and that's what I get. So again, this is concave up right here. But right here, again, it changes, and I'm going to turn it just a little bit because I want to make sure that I actually get the concavity correct in my sketch. And basically, your function looks something like that. Okay, and there's your confirmation. Okay, alrighty. I'm going to go ahead and call this one to a close. We'll do another one in the next video. As always, if you have a question, please do shoot me an email. Bye.